keep having the same conversation.
Here we go. So, if gravity is dependent on mass, why don't heavy objects fall faster than lighter ones? Anybody remember when we talked about this a little bit last year?
Oh, I remember this.
Good guess.
Because they weigh the same.
Doesn't have to do with air resistance.
Acceleration and force stuff.
Yes, Jaden?
Because the difference between the object and the Earth is so great, it doesn't make a difference.
Okay, that's a good one too. The main thing is what Katie said with Newton's second law, F equals ma. So acceleration is equal to force over mass. So if you make your mass go up, your force of gravity is going to go up at the same rate, and that ratio isn't going to change then. So your acceleration is the same whether you increase your mass or you decrease it for that reason. So that's that. Now let's learn about orbital motion. This is the sort of thing that, last year, in the midst of everything from, everything that went on with the virus and all the stuff with getting going with virtual learning, that was not exactly conducive to orbital motion, as you may or may not remember. So I'm just going to give you a short description on what orbit is, and we're going to jump right into orbital motion today. So, who should we have this be?
Katie.
Katie? Okay. So this is Katie. You got to give Katie some hair.
And she's a giant.
Yeah.
Can I have a balloon?
Sure.
Giant with legs here. I feel like you were a giant.
Yay.
So there's Katie with her balloon, and that's only in this hand because the other hand needs to be free, because she is going to be throwing a baseball as hard as she possibly can.
This is the only part I remember about it.
Well, that's the important part.
Baseball in this direction aimed at my skull.
And you can see pretty clearly that this is a geographically correct map of the United States. So this is North America, South America, there's Florida.
Where's North Dakota?
North Dakota's here.
You kind of cut off the northeast of United States.
That's like a giant fish.
No, I didn't.
Yeah,
that's
what I was going to say. It's like a fish.
A giant
Hey,
fish in the
whether or
bottom.
not I cut off the northeast part of the United States is irrelevant, because at least I included Spain and Great Britain and Ireland and
Yep.
Australia.
Yep.
You're welcome.
Canada's about half down. though.
Okay, so Asia just doesn't exist.
Hawaii
then?
doesn't
Hawaii is
matter.
on the other side.
It
So
looks like a
not
giant fish.
there's a big Pacific Ocean right here.
You also forgot about Hawaii.
Hawaii is okay. So here's Katie,
And the Bahamas.
and she throws a baseball as hard as she possibly can, and it doesn't really go too far, but it goes pretty far. I mean, in terms of the world, that's probably about 100 miles or so.
That's at East Point.
Then Katie's like, "Hey, I got to get in shape, even more so than I am, and I'm going to throw this baseball as far as I possibly can next year." So she goes back to the North Pole, meets with Santa for a little bit, and then when she gets around to throwing that baseball, she gets it even further. Maybe it lands right about there. And that's quite a bit further. Now she's throwing it, I don't know, maybe 500 miles or so. So then she's like, okay, I really got to bulk up. So she enlists in Mr. Romano's Speed and Strength program, and she heads back. And she's then able to throw the baseball all the way to the UK. And that's pretty cool. But she's not happy with that. She wants to throw it even further. So she gets juiced up on the roids.
She starts drinking chocolate milk every day.
Yes.
And now she is able to throw the baseball so hard that it lands right about there. So she's really getting that baseball out there. I don't even know what's over here. Indonesia? I don't know. So goes down like this, stops right there. By now she's like, okay, if I'm really going to do this, I'm really going to do this. So she finds the most powerful steroids on the black market, and she gets as bulky as her muscle fibers will allow her. So she throws that baseball as hard as she possibly can one more time, and this time it goes all the way around the world and comes right back to her.
Does it hit her in the back of the head?
It does not pop her
Never had to
balloon.
practice catching. Oh no.
And folks, this is all orbit is. It's something traveling fast enough that it's able to continue moving around the curvature of the object that's trying to pull it in. If she threw it any faster than this last one, it would end up getting a real big orbit, and eventually it would leave the Earth. If she threw it slower like before, it falls in. But orbit is obtained at the very exact speed that you can throw an object where it continues to just constantly fall around the curvature of the object that you're going around. Yeah,
Did she play DDR like once? That's what happened.
perhaps. Perhaps. So that's what orbit is. Questions on what that means? Because the main thing I want you to get out of your minds is the common conception that most people have is like when you go a little bit higher above Earth, that gravity just kind of magically shuts off. That's not what happens. The reason the International Space Station is up there, the reason space shuttles could go up there, is because they were traveling fast enough once they got out beyond our atmosphere that they could go fast enough that, yeah, if they stood still, the Earth would just pull them right in, but they're moving fast enough that they can actually fall around Earth's curvature. By definition, that's what orbit is. It's roughly 18,000 miles an hour or something. So yeah, you got to be booking it in order to be in orbit around the Earth. What's that?
Usain Bolt could just be in orbit around it.
Both could be in orbit?
Usain Bolt.
Oh, yes, he could be.
You know, Usain Bolt, he had a speed ticket in the school zone.
Just the idea of me picking up a baseball, just throw it for whatever
Never mind
reason.
the like black market cereal.
Well, you made it count, Katie. Okay.
Got there.
Label your notes. Orbital motion and gravity. Orbital motion and gravity. Now, we are used to force of gravity being something simple. Mass times 9.8.
This is the other equation.
Oh.
But here's the thing, yeah. That is an estimation for when we're at the Earth's surface. And if we're dealing with things that are in orbit, they're high enough up that that's not accurate anymore. So we have to be more specific. Enter this equation.
I like the other one.
Yeah. So these would be two masses. One of them would usually be the mass of a planet. And this r is the distance from the center of that planet to wherever the object is located.
Hi, Sarah.
Hi,
Hi,
Sarah.
Sarah.
Hey, Sarah. So if we're going to talk about this being for, like, Earth, it would be g times mass of the Earth times the mass of whatever's out there, Katie, divided by the radius of the Earth squared. So I'll just give you these numbers.
All of the examples today are me.
All the examples every day.
Katie is
Okay.
For the
everything.
rest of the year.
Even next year. They have to deal with me.
2035. Alright, and then we throw Katie in this.
It doesn't matter.
Measure halfway. It stays.
I start teaching, I somehow end up teaching here, walk past the literature. So we throw Katie. You're still using me.
I have a teacher, my third grade teacher, he uses a picture of me in the four corners as like a toddler. And just really using it.
Nice. Well, then, Katie, I'd say then we throw Miss Sievert into orbit.
I think it just has to happen.
Yeah.
I think so,
Talk about
too.
it so much, I just gotta do it.
Well, you will be on video forever,
I
so.
suppose. All the
These
virtual
unit, that
things
unit
are
is absolutely very
So these are the values. G is just a constant. You don't have to worry about the units. But mass of the Earth is equal to that. Radius of the Earth is equal to that. They'll be given to you when you need them. but they are also to be found in your textbook.
Is ME that's the mass of Earth?
Yep.
How did they find the mass of Earth?
It's kind of complicated.
I think we've asked
We
this
can-
before, and he's just gone.
we can- Yeah, we'll get into it when we're not recording this stuff. But on the very back flap of your book, you've got the masses of all the planets and the radiuses of all the planets and all the other information you're going to need for this chapter. Right here, back flap of your book. So, a couple other things that you need to write down. Because we're dealing with orbit, we have to be very familiar with some of the laws that define objects that are in orbit, like planets. Planets do not orbit in a perfect circle. They orbit in something called an ellipse. You guys have heard of that.
Isn't it pronounced ellipse?
Well, this should be interesting. I usually would put more information on the screen like this, but because we're recording all these, I've been trying to keep it on the whiteboard. But this is just too much for me to just write on a whiteboard. So Kepler's 3 laws are really what define everything that we deal with in this orbital motion section. Just like Newton's laws define everything from the force sections. So I'll move me as much as I can here. Oh, that works. Okay, so nah. If we had more time, I'd probably have you write them. But they're good to know. Each planet in the solar system moves in an elliptical orbit with the sun at one focus. So it is not something where it's a perfect circle. Although I will say, for trivia's sake, Venus is the orbit that is closest to a circle in our solar system. The radius vector from the sun to any planet sweeps out equal areas in equal times. What the heck does that mean? Let me show you. So what it means is that when an object is orbiting, so this would be the sun, and this would be a planet. If an object is orbiting, then it's going to sweep out equal areas in equal time. So when it gets further away, see how these are triangles that are, longer but thinner? These triangles here would have the same area as these over here. Because, this distance is less for those. This distance here is greater for these. So if they're going to sweep out equal areas in equal times, then this object has to speed up the closer it gets to the object that it's orbiting around. And that's what's going on here. In order to keep these areas and their coverage the same, this object needs to slow down further away because this is a greater distance here, and it has to speed up here because, this is a smaller distance that it's covering. So that's what it means in Kepler's second law, when it sweeps out equal areas in equal time. The main thing you have to remember is that when an object gets closer to the thing that it's orbiting, it speeds up. When it gets further away, it slows down. The biggest example of this is with comets. Comets speed up incredibly when they get close to the sun. Because the example of comets maybe might look something like this. Here's the sun, okay? Comets basically do this. So you can imagine how fast these comets got to be speeding up by the time they get close to the sun like that. That's where Kepler's second law really is apparent. So, Kepler's third law you should memorize this. The square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. I mean, you knew that already, right? Yep. This just sounds like one of those stupid things that means nothing. But we're going to give it some meaning today. So, what are the equations that we have to use when we're dealing with orbital motion? I think that's the last I need that. Yes, it is.
That's really fun.
I would like you to write down circular orbits, please.
This is a horrible version I have to actually keep doing it.
Let's start our discussion here. F equals ma, right?
Yeah.
Yeah, right? Now,
Please tell me this is one of those things where you just go back to one equation every time.
pretty much, actually.
Let's go.
So, force is equal to mass times acceleration. Now, when an object is orbiting, what force or forces act on that object? Gravity, and that's the only thing that's acting. Because once you have it at that certain exact speed, gravity is the only thing that's going to keep it moving in that circle. If gravity stops acting, it's just going to go straight. So, force of gravity is equal to ma. And because we're moving in a circle, what else do we have to change about this? Yep. So, we already redefined force of gravity. I'll keep this small r. And of course, centripetal acceleration is v squared over r. So we kind of have a little starting point here. This is cool. And if we're going to solve for something, generally, what would we be solving for among all those letters? Velocity, yeah. So let's isolate velocity and just see what happens. So this r goes away. This square goes away. This m goes away. That m goes away. So we got g m over r equals v squared. Therefore, how do we get rid of the square? Square root it. So goodbye square. V is equal to this. So what does that v represent? That v represents your orbital velocity, the speed that you must have in order to remain in orbit around a planet or a star or anything else of a certain distance. So this r would be your distance from the center of mass of that object. This is not necessarily just the radius of that object. It's the radius plus how high above the surface you are. Yeah.
So you're saying square root of v equals v.
Yep. So yeah, this is how you find that particular orbital velocity. And again, it is a particular number. This is not a range of like 1,000 meters per second that we're living in here. This is one specific number you have to be at to remain in stable orbit. So let's just do a quick example of this. I'm going to draw the Earth again. We'll say this is the side with no land.
It's, what is it? There's like the idea that before all the continents separated. What's that? It's just the other side.
Pangea, yeah.
Yeah, it's just then, and it's the other side of the world.
Exactly. Actually, if you look at a globe, if you position it just right, you can pretty much, there's a spot where like almost an entire half of the world is just water. I'll show that to you in a little bit, if we have time. So this is the Earth, and this is a little satellite. We'll say that that satellite is 1,000 kilometers above the surface.
The satellite is actually Katie.
Yes. Or it's Katie's balloon.
Oh,
That's
So
so
we get all
sad.
string up
she
there.
lost it when the ball
Yes.
came back on and hit her.
Oh, the ball hit me, and then I lost the balloon.
The
Oh.
ball cut the string. There you go.
So somehow, Katie's balloon, or whatever we want to say that is got in orbit around the world, and it's 1,000 kilometers above the Earth's surface. So my question would simply be, what is the velocity it must have to remain in stable orbit? So it's a pretty quick solution. We have our equation from over here. Orbital velocity is g times m divided by r. So g is always the same. 6.673 times 10 to the negative 11th. Eventually you'll deal with that enough that you'll have it memorized too. M is the mass of the Earth, which was 5.98 times 10 to the 24th. And that's in kilograms. And that would all be divided by the radius of the Earth, 6.37 times 10 to the 6th, and that's in meters. Am I done? No. Yes, you have another 1,000 kilometers. And if we did this in scientific notation, 1,000 kilometers would be 1 times 10 to the 6th meters. And of course, this all has to be under the square root. And you just do the math. And that's how you figure out your orbital velocity. It's just plugging numbers into the equation, and that's all there is to it. Yes?
You still only use a scientific calculator for all this?
Yes. I never use a graphing calculator. I don't remember the last time I used a graphing calculator. It's so much easier to not have to deal with these parentheses everywhere. So if you do this properly on a scientific or graphing calculator, you should get about 7,360 meters per second. And that would be the appropriate orbital velocity to have to stay in orbit at that spot. And again, this is more or less something that you can just leave. Like, space shuttles don't need to continually adjust their orbital velocity because there's no atmosphere out there. There's nothing to slow them down. But if, like, realistically, if Katie was throwing that baseball, air resistance would slow it down and the thing wouldn't work. But if we sucked all the air out, then you get the idea.
We sucked all
Realistically,
the
if Katie was throwing a baseball across
Isn't
the
it
entire
kind of a
world.
famous so like it took away the atmosphere from the Earth? Or like Belgium was about to, but then they stopped it.
Probably.
Yeah, we've all been there.
Questions about this?
I think it actually makes sense.
Good. So let's keep going then.
Harold, Katie, what's up next?
Okay, now Katie has to orbit it.
Can I be the planet that it's orbiting?
Oh.
I am a planet of my own, thank you.
You know, it's kind of interesting. The further you go out, the slower the velocity needs to be for something to be in orbit. So I actually wanted to figure out, like, a standard person with a good arm can probably throw a baseball about 60 miles an hour. So it's like, I wonder how far you could be for that to be the velocity for your orbital speed. And I calculated it one day. You basically have to be out by Jupiter. So it's out there.
Jupiter.
Yeah. Okay.
That's assuming you're going to throw it 60 miles an hour. About 30.
Hey, yo, I'm gonna be like, what's his name?
It's actually plastic. It was in slow motion.
Reputed those black market steroids.
Bro, I'm telling you guys, chocolate milk.
Okay. So, orbital velocity is this. Let's take this one step further, and then we'll actually give some meaning to that sciencey sounding Kepler's third law. So, orbital velocity is equal to this. Now, if something's moving in a circle, I can find velocity in a different way. Velocity is just equal to distance over time, right?
Yeah.
And if you're moving in a circle, what's your distance?
2 pi r.
Yeah, your circumference, 2 pi r, yep. So 2 pi r divided by time, or I'll just keep it capital, because usually that means your period when you're going in a circle like this. So this is our velocity when we're moving in a circle. So we have two equations that mean the same thing. So let's see what Kepler was actually talking about here. let's set these two things equal to each other and use a different color.
So we have to solve for pi?
Everybody on board with why I can set these two things equal?
Yeah.
Because they're both orbital velocities. Good. So if I want to solve, like Kepler's third law says, the square of the orbital period of any planet is proportional to other things. So if I want to solve for the period, I want to solve for time. So let's do that. Let's square both sides first to get rid of that. So that'll be... Did I do that right? I think so.
No.
Okay. So now if I want to solve for time, I'm going to multiply both sides by time. So it's going to come over here. And then I'd have to divide both sides by gm over r, which basically means multiplying this side by the inverse of that. So I'm going to multiply that side by r divided by gm. Does that make sense? Okay. So then if I'm multiplying this side by r over gm, this r is going to now be cubed. And it's going to be divided by gm, yeah. So, this is kind of the funny part. So, this looks like madness. So here's where Kepler's third law comes in. Basically what they say is they say, let's take this here, and we'll set this equal to k.
Constant, you said.
Yes. And now you have Kepler's third law. The square of the orbital period of any planet is proportional to the cube of the semi-major axis, or the long radius, of the elliptical orbit. And we'll get more into examples about this next time. But, you know, as arbitrary as this looks, there's actually a good reason for it, believe it or not. It turns out that under very particular conditions, you can set this equal to 1. And we're going to talk about some of those tomorrow. Yeah?
Well, isn't it r cubed over gm?
What? Well, this whole thing here is equal to k.
Oh.
Yeah. Okay. Last thing we're going to talk about today has a little bit to do with conservation of angular momentum. Any last questions behind this? Okay. Write down conservation of angular momentum. So one thing we have to realize when we're dealing with angular momentum is, part of the definition of angular momentum is that torque is equal to the rate of change of angular momentum. And so let's just briefly talk about torque here. If something is going in orbit around an object or a planet, then torque, remember, is just radius times force. So let's say this is our radius here. What direction is the force of this object at this point? Oh, you're thinking right-hand rule. So think about like the force of gravity. What direction would the force of gravity be pointing here? Opposite what? Yeah, opposite the radius. Because whenever you're moving in a circle, the force is always pointing towards the center of that circle. So force of gravity would be pointing this way. So what does that mean? That means that when we're dealing with torque, which is, radius times force, that's always going to be equal to 0. Because when we're crossing the radius and the force, we're always crossing the portion of the force that's perpendicular. And here it's completely parallel. There is no perpendicular force acting when something is in orbit. So what that means then is that your angular momentum is unchanging. Angular momentum is constant. As long as you're in orbit, that's going to be true. And you dealt with this briefly in the last section, but we'll elaborate more on that here.
I like that I can't tell how many letters are lowercase and constant.
I looked away for 1
Yeah,
minute.
I was like, I got to this point. It seemed like the S was big, so I made the T big. And look at that frilly little A. That's some.
It looks
I
like
think
that
my
Atlanta
favorite
Braves
are
logo.
that there's 2 different ends. And
Yeah, I did change
happy and
ends.
frustrated at the same time.
Wow, I changed
You got
capitalization
excited
mid-word. That is rare. Okay, so we do have a couple minutes. That's good. I just want to talk briefly about derivatives. The reason for that is just because I think it's kind of nice to see where this all comes from, and I want to make sure that you don't think that we're just saying, this is equal to the derivative of that, and it just comes out of nowhere. It's actually a proven thing. You don't have to write this down, but I just kind of want to demonstrate. Like, what's that?
I proved that accidentally on my test a few times.
Yes, you did. I was very proud of you.
I need to start writing stuff that people.
I did the derivative of, I did that. I set this to equal to time in different form, and that acted as MA.
I think I did that too.
So in terms of the torque over here, what was the straight line version of torque? Do you remember? Like if we were dealing in just straight lines and not going in circles last chapter, what did I say is the equivalent of torque?
Force.
Force.
MA.
Yep. And what would the straight line equivalent of angular momentum be?
Momentum.
Regular momentum. So, do you think that force is the derivative of angular momentum?
I bet you it is.
I better absolutely believe that. You're 100% correct. So, because force is equal to ma. And if I take the derivative of momentum, which is mv, the v turns into an a. And the same thing is true here. Torque is equal to radius times force. Force is ma. Angular momentum is rmv. And if you take the derivative of that with respect to time, you get rma. So by definition, these are equivalent. It's not just a relationship that somebody noticed. It's something that's actually derivable mathematically. So yeah, just wanted to show you that. To close out, I think I will show you that the world is pretty much water from one side. And I'm going to show the folks at home.
You're going to show the folks at home?
Now this world is from 1992, so it's still got the USSR. But I don't think the rest of it has changed very much. So I mean, just take a look. That's one side of the world right there. Pretty much all water. The Pacific Ocean is a huge, huge area.
And that's the end of your video.
And that's Hawaii.
And that's how orbital motion